Space, silent, endless, and seemingly empty. But can anything truly come from nothing? To understand how stars are born, we must first peel back the layers of the universe and ask, what do we mean by nothing? Is it the absence of all things, or a hidden ocean of invisible potential? For most of human history, the night sky has appeared eternal and unchanging. Stars were seen as fixed points of light, everlasting lanterns in the firmament. But today, we know the truth is far more dynamic, far more astonishing. Stars are not eternal. They live, they die, and crucially, they are born. But before we can watch a star ignite, we must trace its beginnings back to the raw materials and even further, to the very birth of matter itself. When we gaze into deep space, we often imagine a perfect void, but nothing in cosmology is never truly empty. What looks black and hollow between the galaxies is actually filled with tenuous gas, faint dust, scattered photons, and restless particles. Even the quietest corner of the cosmos still hums with energy, a fabric stretched with quantum fluctuations. This idea is crucial because stars do not literally form out of absolute nothingness. Instead, they emerge from the near-nothing, the sparse, invisible reservoirs of gas and dust left behind by the early universe. To say stars form from nothing is to recognize how astonishingly little is required to spark cosmic fire. Rewind the cosmic clock 13.8 billion years. After the Big Bang, the universe was a sea of particles, protons, electrons, photons, and neutrinos whirling in a hot plasma. For hundreds of thousands of years, no atom, no molecule, and certainly no star existed. It wasn't until about 380, 0 years after the Big Bang, that the universe cooled enough for the first atoms, mostly hydrogen, with a sprinkling of helium to form. This era is called recombination. When electrons pair with nuclei to make neutral atoms, the cosmos then entered a long dark age. No stars, no galaxies, only vast clouds of hydrogen and helium stretching across the infinite universe. It was from this apparent emptiness that the very first stars, the population 3 stars, would emerge hundreds of millions of years later. The secret to turning nothing into something lies in the quiet, relentless pull of gravity. Even the thinnest cloud of hydrogen gas is not perfectly uniform. Tiny fluctuations seeded by quantum variations, magnified during cosmic inflation, left denser patches scattered across the universe. Gravity worked patiently on these regions, tugging on hydrogen atoms one by one, coaxing them closer together. Over millions of years, clouds began to contract. Slowly at first, then faster as density increased. Like a snowball rolling downhill, gravity turned minuscule ripples into massive collapses. These clouds, called nebulae, became the cradles of future stars. Within their folds, the temperature and pressure began to rise. What was once a whisper of particles drifting in the void was becoming a nursery of fire. From a human perspective, this transformation is staggering. Imagine a cubic meter of interstellar space emptier than any vacuum we can make on Earth, containing perhaps just a few hundred atoms. Over eons, gravity can gather those atoms into immense clouds spanning dozens of light years. Within them, billions of trillions of atoms collide, compress, and heat. What was once practically nothing begins to look like something, a luminous embryo hidden in a cocoon of dust. The universe, without design or intention, has sculpted the first sparks of starlight. But to understand this process deeply, we need to slow down and examine the chain of events. How does hydrogen gas collapse into a burning core? What roles do turbulence, magnetic fields, and shockwave play? Why do some clouds produce a single star while others give birth to entire clusters? In this journey, we will unravel the story step by step, from the faint whispers of quantum fluctuations to the swirling disks of gas that circle newborn stars, to the ignition of nuclear fusion itself. Stars, the engines of creation, form not out of abundance, but out of scarcity. They are born from almost nothing. Yet once they ignite, they transform everything, forging heavier elements, shaping galaxies, and ultimately making planets, oceans, and life possible. So how do stars form from nothing? The answer begins not with fire, but with darkness. It begins in the void, a cosmos that seemed empty, but was filled with hidden potential. Through gravity's patient hand, nothing condensed into something. And in the next chapter, we will journey deeper into these clouds of gas and dust to witness how the collapse continues until the first true sparks of starlight appear. The story of stars moves now from the cosmic void into the hidden nurseries where new suns are born. To the naked eye, many of these nurseries appear as dark patches blotting out the background of the Milky Way. To telescopes sensitive to radio waves and infrared light. However, they are revealed as sprawling structures, enormous reservoirs of cold gas and dust. These are molecular clouds, also called stellar nurseries. They are the wombs of creation, where gravity begins its slow, delicate work of turning diffuse hydrogen into blazing stars. Though vast beyond comprehension, these clouds are paradoxically fragile, balanced precariously between collapse and dispersal. A single molecular cloud can stretch for hundreds of light years and contain enough material to form thousands of stars like our sun. Yet they are so diffuse that, if compressed into a solid ball, they would barely occupy the volume of our solar system. From Earth, they appear dark because their dense dust absorbs starlight. In truth, they are not empty at all, but overflowing with potential. The gas within them is mostly hydrogen molecules, cooled to only a few dozen degrees above absolute zero. In this frigid state, atoms can stick together, forming molecules that clump into filaments and knots. These structures are almost invisible without specialized instruments, but they hold the seeds of every future star. To form a star, gravity must overcome resistance. Every gas cloud is in constant motion, with atoms bouncing and colliding, producing internal pressure. Normally, this pressure balances gravity, preventing collapse. So what tips the balance? The answer often comes from disturbances, a nearby supernova explosion sending shock waves through space, a collision between galaxies, or the spiral arms of the Milky Way compressing gas as they rotate. These events squeeze the molecular cloud, raising its density until gravity takes control. Once that threshold is crossed, collapse becomes inevitable. This threshold is known as the Jeans instability. When the mass of a region exceeds a certain limit relative to its temperature, pressure can no longer resist gravity. The cloud begins to contract. What was once a delicate balance tips suddenly into motion, the beginning of star birth. As the cloud contracts, it doesn't collapse into a single object. Instead, turbulence and uneven density cause it to fragment into smaller pieces. Each fragment can form its own star, or in some cases, multiple stars bound together in binary or trinary systems. This is why stars are rarely born alone. Instead, they emerge in clusters, siblings sharing the same molecular womb. Some will remain bound together for billions of years. Others will drift apart into the galaxy. But for now, they are family, bound by a common origin in the dark, cold cloud. As collapse continues, the fragments, called dense cores, shrink and heat up. Deep within them, gravitational energy converts into thermal energy. The temperature climbs, but the thick shrouds of dust around the cores hide the light, cloaking the process in mystery. To us, these dense cores are invisible light. But to infrared telescopes, they glow faintly, like embers buried under ashes. This glow is the first whisper of a new star, a secret beacon hidden from ordinary sight. The birth of a star is not simply gravity crushing matter into a ball. Magnetic fields thread through molecular clouds, guiding and resisting the collapse. They channel gas into long filaments, shaping the geometry of stellar nurseries. At the same time, turbulence stirs the gas like boiling water, creating eddies and swirls that compete with gravity. These chaotic motions delay collapse in some regions while accelerating it in others. The result is a complex, dynamic environment where chance and physics intertwine. For us, the night sky feels eternal. But for the universe, star birth is a relatively swift event. From the moment a dense core begins collapsing, it may take only a few 100,000 years for a protostar to emerge, a blink of cosmic time. Still, to human imagination, hundreds of thousands of years is almost unfathomable. Imagine a single human family passing down stories for 10,000 generations while, above them, a single patch of dark sky slowly transforms into a newborn star. That is the pace of stellar creation. Within the heart of each dense core, temperatures continue to rise. The core spins as it contracts, and conservation of angular momentum causes surrounding gas to flatten into a rotating disk. This is the same disk from which future planets may one day form. The stage is set. The cold, dark, molecular cloud has given way to glowing, spinning embryos, protostars. They are not yet true stars, for nuclear fusion has not begun. But the path is clear. Collapse will continue until the pressure and temperature in the core reach a breaking point. Soon, gravity's patient work will culminate in the greatest transformation of all the ignition of starlight. Inside the darkness of molecular clouds, fragments have collapsed into dense cores. These are no longer mere clouds of gas, but concentrated pockets of matter, the embryos of stars. Invisible to human eyes, they lurk behind veils of dust, waiting to be unveiled. At this stage, we call them protostars, the very first chapter of stellar life. As the dense core collapses under gravity, its atoms crowd together, moving faster and faster. The gas heats up, forming a central knot of material. Though the protostar is only a few tens of thousands of years old, it already has a defined presence, a growing sphere surrounded by a swirling disk of gas and dust. Unlike mature stars, a protostar does not shine from nuclear fusion. Its light comes from gravitational energy. As matter falls inward, potential energy transforms into heat and faint radiation. To distant observers with the right instruments, a protostar appears as a faint, reddish glow, a whisper of what is to come. Around every forming star lies a disk, a flat, rotating structure made of gas and dust. This is the accretion disk, born from the conservation of angular momentum. As gas spirals inward, it can't fall straight into the protostar. Instead, it flattens into a disk, orbiting like water swirling down a drain. These disks serve two crucial purposes. First, they act as a supply line, feeding material into the protostar. Second, they become the birthplaces of planets, moons, asteroids, and comets. In fact, every planet in our solar system began as dust in an accretion disk around the young sun. Thus, in the act of star birth, the seeds of planetary systems are planted. Stars and their worlds are born together. As a protostar grows, it doesn't simply swallow everything. Powerful magnetic fields funnel some material along the poles of the star, launching it outward in high-speed jets. These bipolar outflows carve through the surrounding gas, creating spectacular structures visible in astronomical images. These jets may seem destructive, but they serve a purpose. They help regulate the growth of the star. By ejecting angular momentum and excess matter, they prevent the protostar from spinning apart or becoming unstable. In short, jets are a cosmic balancing act, violent yet necessary. At this stage, the protostar is a battleground between competing forces. Gravity pulls inward relentlessly, squeezing the core tighter and tighter. Pressure, generated by heating gas, pushes outward. The accretion disk delivers fresh fuel, while jets expel it. The star is not yet stable, it is still finding itself, still growing into maturity. This phase can last for hundreds of thousands to a few million years. Compared to the billions of years a mature star may live, it is a brief, turbulent adolescence. Yet, in this time, the protostar undergoes enormous changes. Most protostars remain invisible to ordinary telescopes because of their dense cocoons of dust. To study them, astronomers turn to radio and infrared observatories, which can pierce the shrouds. Instruments like the Atacama Large Millimeter Submillimeter Array, ALMA, have given us breathtaking glimpses into these hidden nurseries. Through these eyes, we've seen disks in exquisite detail. Even spotting the gaps and rings where new planets are beginning to form, we've observed jets blasting through space at hundreds of kilometers per second. The once invisible has become visible, revealing the earliest stages of cosmic creation. But the protostar is not yet a star. For that, one more threshold must be crossed: nuclear ignition. As matter continues to pile into the core, the temperature and pressure soar. At around 10 million Kelvin, hydrogen nuclei gain enough energy to overcome their natural repulsion and fuse into helium. This moment, the start of hydrogen fusion, is the true birth of a star. For the first time, energy is generated not by collapse, but by fusion at the core. The outward pressure from fusion balances gravity's inward pull. The star stabilizes. When this balance is achieved, the protostar graduates to the next stage, the main sequence, where it will spend most of its life shining steadily. But before that stability, the protostar must endure turbulence, flickering between bursts of growth and periods of calm, until finally, the fusion fire is lit. Imagine the universe before stars, darkness, silence. Then, in hidden nurseries, protostars gather in mass until, one by one, their cores ignited. The darkness was broken. The first stars poured light into the cosmos, ending the age of darkness and beginning a new epoch. From a near nothingness of cold hydrogen gas, stars were born. Each protostar was a promise that the universe would not remain empty forever, but would blaze with light, color, and eventually, life. In the dark cocoon of the protostar, gravity has done its patient work. Atoms have been pulled closer, collisions have become more frequent, and heat has climbed to unimaginable levels. Now, the stage is set for the most important transformation in cosmic history, the ignition of nuclear fusion. This is the moment when a protostar becomes a true star. At the heart of the collapsing core, the temperature soars above 10 million degrees Kelvin. At such extremes, hydrogen nuclei, simple protons, move with ferocious speed. Ordinarily, the electric repulsion between positively charged protons would keep them apart. But in this furnace, collisions are so violent that protons are forced close enough for the strong nuclear force to take over, binding them together into helium. This process releases staggering amounts of energy, far more than any chemical reaction could ever produce. Each fusion event liberates energy in the form of high-energy photons and neutrinos. Multiplied by trillions upon trillions of reactions happening every second, the core blazes to life. Up to this moment, the protostar's life has been unstable, a tug-of-war between inward-pulling gravity and outward-pushing pressure from heated gas. Fusion changes everything. The energy pouring from the core generates outward pressure powerful enough to balance gravity's relentless collapse. This state of balance is called hydrostatic equilibrium. From now on, the star exists in a stable configuration. Gravity squeezes inward, but radiation pressure and thermal pressure push outward in perfect harmony. The battle has ended, and the star has been born. With fusion ignited, the star enters the main sequence, the long middle chapter of its life. How long it stays here depends on its mass. Massive stars burn brightly but briefly. Their enormous gravity compresses their cores so intensely that fusion runs at a furious pace. They shine millions of times more brightly than the sun, but exhaust their fuel in only a few million years. Smaller stars like our sun burn more moderately. They can remain in the main sequence for billions of years. The smallest red dwarfs sip their fuel slowly, glowing faintly but enduring for trillions of years longer than the universe has currently existed. The main sequence is the era of stability, when the star quietly fuses hydrogen into helium, producing light, warmth, and life-giving radiation. The moment the first stars ignited, the universe changed forever. Before them, the cosmos was a sea of darkness, filled only with cold hydrogen and helium. When the first stars blazed, they flooded space with ultraviolet radiation, ionizing surrounding gas and ending the cosmic dark ages. These ancient giants, the population 3 stars, were unlike stars today. They contained almost no heavier elements, for none yet existed. They were massive, hot, and short-lived, but they forged the first heavy elements in their cores. When they died, they scattered those elements across the cosmos, seeding the raw material for future generations of stars, planets, and eventually life. Inside every main sequence star, fusion follows the cycle. In smaller stars like the Sun, the proton-proton chain dominates. Hydrogen fuses step by step into helium, releasing energy at each stage. In larger stars, a different process, the CNO cycle, carbon, nitrogen, oxygen, takes over, fusing hydrogen more efficiently at higher temperatures. Regardless of the mechanism, the result is the same. Hydrogen fuel slowly transforms into helium, and energy streams outward from the core to the surface, then radiates into space as light and heat. Every sunrise on Earth is powered by this engine, a reminder that our sun is one among countless fusion fires scattered across the Milky Way. The position of a star on the main sequence is determined almost entirely by one thing: its mass. A star's mass dictates its temperature, brightness, lifespan, and ultimate fate. Astronomers summarize this with the phrase, "Mass is destiny." A star more massive than the Sun will be hotter, bluer, and shorter-lived. A less massive star will be cooler, redder, and longer-lived. The Sun, lying in the middle, glows as a yellow-white star with a main sequence life of about 10 billion years. Our star is about halfway through its main sequence journey. It has burned hydrogen steadily for 4.6 billion years and will continue to do so for another 5 billion. Without the stability of the main sequence, life as we know it would never have been possible. Planets orbiting young protostars endure violent outflows and unstable light. But once a star enters the main sequence, its output becomes steady, reliable, and predictable conditions, essential for life to evolve on surrounding worlds. The Sun's long period of stability has allowed Earth to develop oceans, atmospheres, and ecosystems. Every breath we take, every heartbeat, every moment of life on this planet is powered by the quiet, unbroken burning of hydrogen deep within the Sun's core. We began with nothing more than cold hydrogen atoms drifting in space. Gravity gathered them, collapse heated them, and now fusion has ignited them. The void has transformed into light. The star, once a hidden protostar, now blazes openly in the cosmos, a beacon of creation. The journey does not end here. Though the main sequence is long, it is not eternal. Eventually, the balance will shift. Hydrogen will run low, helium will accumulate, and the star's stable glow will begin to falter. What happens then? The next chapters in the star's life hold drama, expansion, and sometimes catastrophic endings. But for now, we linger in the quiet brilliance of the main sequence, the chapter of cosmic stability, the golden age of starlight. For millions, billions, or even trillions of years, a star resides on the main sequence, steadily converting hydrogen into helium. This is the golden age of a star's life, marked by balance and stability. But no fuel lasts forever. Eventually, the hydrogen at the core dwindles. When this happens, the equilibrium that sustained the star begins to break. The star enters a new, unstable phase of its journey, one that leads to transformation, expansion, and in some cases, explosive endings. Fusion in the main sequence relies on hydrogen in the core. Over time, helium ash accumulates there. Unlike hydrogen, helium cannot fuse at the star's current temperature and pressure. Eventually, hydrogen in the core becomes depleted. When this happens, fusion ceases in the central region. Without the outward pressure from fusion to counterbalance gravity, the core contracts under its own weight. As the core shrinks, its temperature rises dramatically. Around this contracting helium core, a thin shell of hydrogen continues to fuse into helium, creating new dynamics inside the star. The increased energy from the hydrogen shell pushes against the star's outer layers. These layers expand outward, cooling as they swell. A star that once shone as a compact, stable sphere now balloons into a much larger object, a red giant. Our Sun, for instance, will one day undergo this transformation. After exhausting its core hydrogen, it will expand to a size so large that its outer layers may engulf Mercury, Venus, and possibly Earth. The Sun's once gentle light will swell into a bloated, fiery glow. A red giant looks dramatically different from its main sequence predecessor. Though its surface temperature is cooler, giving it a reddish hue, its sheer size makes it far more luminous. It shines thousands of times brighter than before, but its internal structure is unstable. Inside, the contracting helium core grows ever hotter. When it reaches about 100 million Kelvin, helium nuclei can overcome their mutual repulsion and begin to fuse into carbon and oxygen. This process, known as the triple alpha reaction, marks the next great milestone in stellar evolution. For stars like our Sun, the onset of helium fusion is violent. The degenerate helium core does not expand smoothly when fusion ignites. Instead, it undergoes a runaway reaction called the helium flash, releasing an enormous burst of energy. Though invisible to outside observers, this event radically alters the star's core, expanding it and stabilizing helium fusion. For a time, the star settles again. Now powered by helium fusion, in its core and hydrogen fusion in the surrounding shell. This is a new stage of equilibrium, but it cannot last forever. Helium, too, will run out. Not all stars evolve alike. Mass is the key. Low-mass stars like red dwarfs never reach the conditions needed for helium fusion. They burn hydrogen slowly for trillions of years and eventually fade into white dwarfs without ever becoming red giants. Medium-mass stars like the Sun expand into red giants, ignite helium, and later shed their outer layers, leaving behind white dwarfs. High-mass stars follow a much more dramatic path. After burning hydrogen, they ignite helium easily, then progress to fusing heavier and heavier elements, carbon, neon, oxygen, silicon, until iron forms in their cores. At that point, their evolution ends in spectacular explosions, supernovae. Thus, a star's mass decides not only its brightness and lifespan, but also its final destiny. The transition from main sequence to giant phase may seem destructive, but it is also creative. As stars swell and shed their outer layers, they enrich the interstellar medium with elements forged in their cores. Carbon, nitrogen, and oxygen, essential ingredients for life, are released into space. When the first generation of stars ended their lives, they seeded the cosmos with these elements, making possible the chemistry of planets and living organisms. Every breath we take carries atoms once forged in dying stars. 5 billion years from now, the Sun will leave the main sequence. Its hydrogen core will be exhausted, and it will swell into a red giant. The Earth, if it survives engulfment, will be scorched into a barren rock. Eventually, the Sun will shed its outer layers into space, forming a glowing planetary nebula. The remaining core will contract into a dense white dwarf, slowly cooling for trillions of years. For our star, the end will not come in a violent supernova, but in a graceful fade into cosmic quiet. Yet, even in its death, the Sun will release material that may one day form new stars and planets. The post-main sequence evolution of stars shows us a deeper truth. Stars are not static beacons, but dynamic engines of change. Their lives are cycles of ignition, balance, exhaustion, and renewal. The nothing from which they were born transforms into light, then into heavier elements, and finally into the raw materials for new stars and worlds. The story of stellar evolution is, in essence, a story of recycling. Matter is never destroyed. It is reshaped, reconfigured, passed from one star to the next, one generation to another. From the death of stars comes the possibility of future suns and, perhaps, future life. Not all stars go out with a bang. For the majority of stars in the universe, including our Sun, the end is marked not by violent explosions but by a quiet shedding of layers, a fading into darkness. These stars may not collapse into neutron stars or black holes, but their final chapters are no less important. Their endings provide the cosmos with the raw ingredients of life. After a star like our Sun completes the fusion of helium into carbon and oxygen, its fuel once again runs low. The core contracts further, heating up, but for stars of modest size, the temperature never becomes high enough to ignite carbon fusion. Instead, the outer layers of the star grow unstable. Pulsations and stellar winds drive gas away into space. Over tens of thousands of years, the star sheds much of its mass, casting off shells of material into the void. This process creates spectacular structures called planetary nebulae. Despite the name, they have nothing to do with planets. Early astronomers, peering through small telescopes, thought their round shapes resembled planets, and the term stuck. Planetary nebulae are among the most beautiful objects in the universe. Expanding shells of gas glow with vivid colors as ultraviolet light from the exposed core ionizes them. Some appear as rings, others as butterflies, still others as delicate wisps, each shaped by the complex interplay of magnetic fields, stellar winds, and binary companions. These glowing clouds may last only 20, 0 to 50 years, a fleeting moment compared to a star's billions of years of life. Yet in that time, they scatter essential elements, carbon, nitrogen, oxygen, across interstellar space. What once resided in the star's core is now free to mix with gas and dust, ready to form new generations of stars and planets. When the outer layers drift away, what remains is a hot, dense core of the star. no longer sustaining fusion. It glows faintly from leftover heat. This remnant is called a white dwarf. A white dwarf is tiny compared to its progenitor. Roughly the size of Earth, it contains about half the mass of the Sun compressed into that small volume. Its density is staggering. A teaspoon of white dwarf matter would weigh several tons on Earth. White dwarfs shine not because they generate energy, but because they slowly cool over time. At first, they glow brilliantly white, but as billions of years pass, they fade to red, then infrared, and finally into darkness. There is a natural mass boundary for white dwarfs known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. Stars less massive than this can leave behind white dwarfs. But if a stellar remnant exceeds this limit, gravity overwhelms electron degeneracy pressure, the quantum mechanical effect that supports white dwarfs against collapse. Such stars cannot become white dwarfs. Their fate lies in supernovae and denser objects like neutron stars or black holes. This limit explains why only low and medium mass stars end quietly. The heavyweights live and die by more violent rules. Our own sun is destined to follow this gentle path. After swelling into a red giant and shedding its outer layers, it will form a glowing planetary nebula, visible for a brief cosmic moment. At its center will remain a white dwarf, slowly cooling over trillions of years. This quiet ember will never collapse further, for its mass lies comfortably below the Chandrasekhar limit. Eventually, it will cool into a theoretical black dwarf, a star that has lost nearly all its heat and no longer emits visible light. No black dwarfs exist yet, for the universe is not old enough. But given enough time, they will fill the cosmos like scattered relics of a bygone age. Though less dramatic than supernovae, the deaths of low and medium mass stars are vital to cosmic evolution. The planetary nebulae they create enrich the interstellar medium with carbon and oxygen, the building blocks of life. Without these quiet deaths, there would be no organic molecules, no rocky planets, no humans to ponder the stars. Each breath we take contains oxygen forged in ancient stars like the Sun. Each atom of carbon in our bodies was once part of the core of a dying star. To say we are made of star stuff is not poetry, it is scientific fact. White dwarfs remind us that the universe is not only a place of violent change, but also of long, slow fades. These remnants will outlast most other stellar objects, cooling quietly while galaxies evolve, merge, and transform. Long after the Sun's planetary nebula has faded, its white dwarf will drift through the Milky Way, a silent witness to the changing cosmos. The story of quiet stellar deaths is one of beauty and legacy. Though these stars end without explosions, they leave behind more than light. They leave the very matter from which life arises. Not all stars fade quietly into the dark. For the universe's giants, death is not a gentle release, but a cataclysm. These massive stars, many times larger than the Sun, live fast and die young. When their fuel is gone, they collapse and explode with a violence so intense that they briefly outshine entire galaxies. In their final moments, they forge the heaviest elements and scatter them across space. These are the supernovae, the universe's most spectacular fireworks. Stars with at least 8 times the mass of the Sun live dramatically different lives from smaller stars. Their cores reach higher pressures and temperatures, enabling them to fuse not just hydrogen and helium, but progressively heavier elements: carbon, neon, oxygen, silicon. Each stage of fusion creates a new layer, like the layers of an onion. At the core lies iron, the dead end of fusion. Unlike lighter elements, fusing iron consumes energy instead of releasing it. Once iron builds up, the star's engine sputters. Fusion halts. When fusion stops, nothing can counteract gravity. The iron core collapses in less than a second, shrinking from thousands of kilometers wide to just tens. Temperatures soar to billions of degrees, and densities exceed that of atomic nuclei. As the core collapses, electrons and protons are crushed together to form neutrons. Neutrinos stream outward in unimaginable numbers, carrying away vast amounts of energy. For an instant, the collapsing core rebounds, sending a shockwave through the star. This shockwave, energized by escaping neutrinos, blasts the star apart in a supernova explosion. In that moment, the star shines brighter than the rest of its galaxy combined. Material is hurled into space at thousands of kilometers per second. Supernovae are rare in any one galaxy, occurring perhaps once a century, but across the cosmos, they happen every second. They are nature's foundries, forging elements heavier than iron, gold, uranium, platinum, and scattering them across interstellar space. Every piece of jewelry, every nuclear reactor, every red blood cell carrying iron owes its existence to these cosmic blasts. If the collapsing core is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These objects pack more mass than the Sun into a sphere just 20 kilometers across. Their density is almost incomprehensible. A teaspoon of neutron star matter will weigh billions of tons on Earth. Neutron stars have extreme properties. Their magnetic fields are trillions of times stronger than Earth's. Many spin rapidly, emitting beams of radiation that sweep across space like lighthouses. We call these objects pulsars, and they were first detected in 1967 as mysterious, regular radio pulses. If the collapsing core exceeds about 3 solar masses, not even neutron degeneracy pressure can resist gravity. The core continues collapsing, shrinking into a point of infinite density, a black hole. Black holes warp space-time so strongly that nothing, not even light, can escape once it crosses the event horizon. To the outside universe, the star has vanished, leaving only a region of darkness surrounded by distorted starlight. Though invisible, black holes reveal themselves through their effects. Gas spiraling into them heats up and emits powerful X-rays. Binary companions caught in their grip betray their presence. And on cosmic scales, supermassive black holes, millions to billions of times the sun's mass, lurk at the centers of galaxies, shaping their evolution. The violent deaths of massive stars are not just destructive, they are essential to cosmic evolution. By scattering heavy elements, supernovae enrich the interstellar medium, allowing future generations of stars and planets to form with the building blocks of life. Without supernovae, there will be no Earth, no oceans, no DNA, no humans. The calcium in our bones, the iron in our blood, the gold in our rings, all were forged in the fiery deaths of massive stars. Quiet deaths produce white dwarfs and planetary nebulae, beautiful but gentle. Violent deaths produce neutron stars and black holes, exotic remnants that push physics to its limits. Together, these endings reveal the dual nature of the cosmos: serene and violent, peaceful and catastrophic. The universe is not static. It is a place where stars are born, shine, and die in endless cycles. And from these cycles, new worlds and new possibilities emerge. When we look up at the night sky, every star we see will one day die. Most will fade quietly, but some will erupt with unimaginable violence. Their deaths remind us that destruction and creation are inseparable in the cosmos. From the ashes of dead stars come the seeds of new stars, new planets, and new life. Supernovae, neutron stars, and black holes are not merely the end of stellar evolution. They are gateways to the future, ensuring that the universe remains dynamic, evolving, and filled with possibility. The life and death of stars do not happen in isolation. Each birth, each explosion, and each remnant contributes to the grand architecture of galaxies. Stars may seem like individual points of light scattered across the sky, but together they form vast ecosystems, where the death of one star seeds the birth of another, and the remnants of stellar lives regulate the growth of galaxies themselves. Between the stars lies the interstellar medium, a mixture of gas, dust, radiation, and magnetic fields. It may appear empty, but it is the very substance from which new stars are born. Supernovae, stellar winds, and dying stars constantly enrich and reshape this medium, ensuring that galaxies are not static star collections but dynamic, evolving systems. Every star, no matter how it dies, feeds back into this medium. Planetary nebulae from low-mass stars return carbon and oxygen. Supernovae from massive stars eject iron and heavier elements. Stellar winds carry dust and gas into surrounding space. Galaxies breathe with the rhythm of these processes, inhaling gas to form new stars. exhaling enriched material through stellar deaths. Supernovae are more than cosmic fireworks, they are engines of feedback. When a massive star explodes, it releases energy equivalent to the sun's output over its entire lifetime, all in a matter of seconds. This energy races outward as shock waves, compressing some regions of the interstellar medium while dispersing others. In dense areas, shock waves trigger star formation by compressing gas clouds until they collapse. In diffuse regions, shock waves disperse gas, halting star formation by blowing material away. This push and pull process regulates a galaxy's growth. Without feedback, galaxies would form stars too quickly and burn through their gas in a short burst. With feedback, star formation becomes a self-regulated cycle, stretched across billions of years. Stellar deaths also transform the chemical composition of galaxies. The earliest stars contain only hydrogen and helium, the primordial elements of the Big Bang. Each generation of stars adds new ingredients: carbon for organic molecules, oxygen for water and air, iron for planets' cores and human blood, gold and uranium for Earth's crust and our technologies. Over billions of years, galaxies become chemically richer, able to form rocky planets and complex molecules. The Milky Way, now over 13 billion years old, is a galactic cauldron seasoned by countless stellar lives and deaths. Perhaps the most dramatic influence on galaxies comes from black holes, especially the supermassive black holes lurking at galactic centers. These monsters, millions or billions of times the mass of the Sun, are thought to grow from smaller black holes formed by stellar collapse. When matter falls into them, it doesn't simply vanish. Before crossing the event horizon, gas swirls into an accretion disk, heating up to extreme temperatures and emitting powerful radiation. Jets of energy and particles can blast outward across thousands of light years. This feedback can regulate star formation on galactic scales. Too much gas falling into the black hole, jets and radiation can blow it away, quenching star formation. Gentle accretion, the energy stirs the interstellar medium, preventing collapse but leaving enough material for stars to form slowly. In this way, black holes are paradoxical creators. By consuming matter, they control the pace at which galaxies grow and evolve. The deaths of stars also influence how galaxies are structured. Supernovae carve out superbubbles in the interstellar medium, enormous cavities surrounded by glowing shells of gas. Over time, these cavities merge, helping to create the spiral arms of galaxies like the Milky Way. Meanwhile, star clusters, groups of stars born together in molecular clouds, gradually disperse, their remnants scattering throughout the galaxy. Some remain gravitationally bound for billions of years, becoming globular clusters, relics of the earliest star formation. Thus, stellar evolution not only enriches galaxies chemically, but also sculpts their very shapes. Galaxies are ecosystems, and stars are their lifeblood. The birth of stars consumes gas. Their lives radiate energy. Their death return enriched material, and their remnants regulate the cycle. The feedback loops of stellar evolution ensure that galaxies remain dynamic, diverse, and capable of producing complex structures like planetary systems. In this way, stars are both products of galaxies and their architects. Without the push and pull of supernovae, stellar winds, and black holes, galaxies would be barren, static islands of gas. Instead, they are vibrant, ever-changing structures, the cosmic cities where billions of suns rise and die. When we look at the Milky Way stretching across the night sky, we are seeing not just a collection of stars, but a living system. The Sun, the Earth, and all life are part of this galactic cycle. We were born from gas enriched by ancient stars, and one day, the Sun will return its own material to the interstellar medium, continuing the cycle for future generations. In a real sense, we are participants in the breathing of the galaxy. We inhale the oxygen forged in dead stars, and when we exhale carbon dioxide, those atoms may someday drift into space, to be woven into new stars, planets, and perhaps new beings. The remnants of stars are not simply corpses. They are creators. They shape galaxies, regulate star formation, and ensure the cosmos is always evolving. In their death, stars write the future of the universe. Though we often imagine stars as solitary, like our sun drifting alone through the Milky Way, Most stars begin their lives not in isolation, but as members of families. Born together in giant molecular clouds, they emerge in groups of dozens, hundreds, or even millions. These stellar family star clusters are key to understanding how stars form, evolve, and shape galaxies. When a molecular cloud collapses, it rarely forms just one star. Instead, turbulence, magnetic fields, and fragmentation break the cloud into many dense cores, each of which can ignite as a star. The result is a cluster, a stellar nursery filled with siblings sharing a common origin. Star clusters are laboratories of astrophysics. Because all their stars form at roughly the same time and from the same material, they allow astronomers to study how differences in mass alone affect stellar evolution. By comparing the stars in a cluster, we see directly how mass shapes destiny. The most familiar type of cluster is the open cluster. These are loose associations of a few hundred to a few thousand stars, bound together only weakly by gravity. They are young, typically less than a few 100 million years old, and many still contain leftover gas and dust from their birth. The Pleiades, or Seven Sisters, is a famous example visible to the naked eye. In reality, it contains over 1,000 stars, still drifting together through space. Over time, however, tidal forces from the galaxy pull these clusters apart. Most open clusters eventually dissolve, their stars scattering into the galactic disk. Thus, while open clusters are common sites of stellar birth, they are temporary. They represent the adolescence of stars groups that will eventually drift apart into the wider galactic population. In contrast, globular clusters are dense, spherical collections of hundreds of thousands to millions of stars. Unlike open clusters, they are ancient, among the oldest structures in the universe. Many globular clusters in the Milky Way are more than 12 billion years old, nearly as old as the galaxy itself. These clusters orbit the Milky Way's halo, far above and below the galactic disk. Their stars are typically metal-poor, meaning they form from primordial gas with few heavy elements. This tells astronomers that globular clusters are relics of the earliest star formation, fossils from a time before the universe was enriched by many generations of supernovae. Globular clusters are also extraordinary environments. Stars are packed tightly together, sometimes just a fraction of a light year apart. Stellar encounters and interactions are far more common here than in the sparse neighborhoods around stars like our Sun. By studying clusters, astronomers classify stars into stellar populations, broad groups based on their age and chemical composition. Population I stars are young, metal-rich stars like the Sun found in the galactic disk. Their composition reflects billions of years of enrichment from earlier generations. Population II stars are older, metal-poor stars, common globular clusters, and the galactic halo. They formed early, before many heavy elements were available. Population III stars, the very first stars, remain hypothetical, as none have yet been directly observed. They would have been entirely metal-free, made only of hydrogen and helium from the Big Bang. This classification allows astronomers to trace how galaxies evolved chemically and dynamically, showing us how the universe moved from simple beginnings to the complexity we see today. One of the most powerful tools in astronomy is the Hertzsprung-Russell diagram, a plot of stars' brightness against their temperature. When astronomers place stars from a cluster on this diagram, a clear pattern emerges. Because all stars in the cluster form at the same time, the point at which stars leave the main sequence reveals the cluster's age. This method has allowed us to determine that globular clusters are among the oldest objects in the universe, helping constrain the age of the cosmos itself. Star clusters, in this way, act as cosmic clocks. Clusters are also important for understanding the origins of planetary systems. Recent discoveries show that planets can form even in dense clusters, though their survival depends on the environment. In crowded globular clusters, close stellar encounters may disrupt planetary orbits. In looser open clusters, planets have a better chance of stability. Our Sun likely formed in an open cluster about 4.6 billion years ago. Though its stellar siblings have long since drifted apart, they remain scattered across the Milky Way. Somewhere out there, Stars born alongside the sun still shine, distant family members lost in the crowd. Open clusters eventually dissolve, their stars absorbed into the galaxy. Globular clusters, however, are remarkably resilient. Their dense gravitational binding allows them to survive for billions of years, orbiting silently as ancient witnesses to galactic history. Yet, even globular clusters are not eternal. Over cosmic timescales, tidal interactions with galaxies and the pull of dark matter may eventually tear them apart. Still, their long lives ensure that they remain as fossils of the early universe, preserving information no longer available elsewhere. Star clusters remind us that stars are not merely isolated points, but part of greater communities. They form together, evolve together, and in some cases, endure together for nearly the entire age of the universe. When we look at the Pleiades in the winter sky or at the dense swarm of Omega Centauri through a telescope, we are glimpsing stellar families, the siblings of the cosmos. They show us that even in the vast emptiness of space, stars are born not in solitude but in company, sharing their first moments in clusters before dispersing into the galaxy. Stars are not only the luminous threads that decorate the universe, but also its clocks recording the tempo of cosmic history. Just as individual stars live and die over millions or billions of years, the universe itself has gone through epochs of furious creation and quieter times. The rate at which galaxies have formed stars is not constant. It has ebbed and flowed, following a cosmic rhythm that tells a story of how the universe evolved. For hundreds of millions of years after the Big Bang, the universe was dark. Hydrogen and helium filled space, but no stars yet burned. This period, known as the Cosmic Dark Ages, ended when gravity gathered gas into the first halos of dark matter, leading to the birth of the first stars, population 3 stars. These pioneers were massive, bright, and short-lived. They formed in small numbers around 100 to 200 million years after the Big Bang, and their deaths seeded the cosmos with the first heavy elements. Though rare and fleeting, they ignited the universe, starting the story of cosmic star formation. As the universe aged, galaxies grew by merging and gathering gas. Between 2 and 3 billion years after the Big Bang, star formation reached its peak. This epoch is sometimes called Cosmic Noon, when the universe was most active in creating stars. During this time, galaxies churned out stars at astonishing rates. Massive galaxies formed hundreds of solar masses of stars each year, far more than the steady pace of the present Milky Way. Collisions and mergers fueled this frenzy, compressing gas into dense starburst regions. If we could look at the sky during this golden age, it would appear far brighter, with galaxies blazing with newly formed stars. It was a universe in bloom, the prime of cosmic creativity. After this peak, the rate of star formation began to decline. By 5 billion years after the Big Bang, galaxies were forming stars at only a fraction of their earlier pace. Several factors contributed to this slowdown. Gas depletion. Much of the raw hydrogen in galaxies had already been consumed or expelled. Heating of the intergalactic medium. As more stars and black holes formed, their radiation heated surrounding gas, making it harder for fresh gas to cool and collapse. Feedback processes. Supernovae and black hole activity drove winds that blew gas out of galaxies, reducing star-forming fuel. Over billions of years, these processes gradually starved galaxies of the cold gas needed to make new stars. Today, more than 13 billion years after the Big Bang, the universe is a calmer place. Star formation still happens, but at a fraction of its former glory. The Milky Way produces a few new stars per year, a gentle hum compared to the roar of cosmic noon. Most elliptical galaxies have shut down entirely, glowing faintly with ancient stars but forming no new ones. Spirals like the Milky Way and Andromeda continue steadily, while dwarfs still contribute small but important bursts of creation. We live in a time of decline, the twilight of star formation. Yet this quieter pace has advantages. It allows stable environments for planetary systems to develop and for life to flourish without the constant bombardment of massive starbursts and supernovae. What lies ahead for the universe's stellar production? Predictions suggest a slow fade. As galaxies consume or lose their remaining gas, star formation will dwindle further. In tens of billions of years, galaxies will form only a trickle of stars. using up their last reserves. In hundreds of billions of years, new star formation will cease almost entirely. Red dwarfs, the most numerous and long-lived stars, will continue to burn faintly for trillions of years, keeping the universe lit even after most stellar factories shut down. Eventually, the cosmos will enter a dark age once again, this time permanent when no new stars can form, and only remnants like white dwarfs, neutron stars, and black holes remain. When we step back and look at this grand history, a pattern emerges. The universe begins with darkness. The first stars ignite, seeding the cosmos with light and elements. Star formation rises to a peak, a cosmic bloom of creation. Gradually, the pace slows, leading to the quieter universe we see today. In the far future, the lights will fade as the last stars burn out. This rhythm from dark to bright to dark again defines the cosmic story. It shows us that star formation is not eternal, but part of a larger cycle that shapes the destiny of everything we know. Human beings exist at a special point in this history. We live after the peak of star formation, when enough generations of stars have created the heavy elements for planets and life, but before the universe has grown too old and quiet. The sun, the earth, and humanity are products of a universe at just the right stage, rich in elements, steady in star formation, and stable enough for life to evolve. We are children of the cosmos, born in its middle age, able to look back on its fiery youth and forward to its quiet future. The history of cosmic star formation is not only the story of stars, but of us. Every atom in our bodies carries the record of this rhythm forged in ancient stars, enriched by supernovae, and assembled in a galaxy that has been creating stars for billions of years. Though our sun appears alone in space, it is something of an outlier. Most stars in the universe are not solitary wanderers, but part of binary systems, pairs of stars bound together by gravity, orbiting a common center of mass. Some even form multiple systems with 3 or more companions, weaving a gravitational dance. Binary stars are not just curiosities. Their interactions create many of the universe's most dramatic events, from novae that flare suddenly in brightness to the Type Ia supernovae that serve as cosmic mile markers. By studying binaries, astronomers uncover new insights into stellar evolution and the forces that shape galaxies. A binary system may consist of 2 stars nearly identical in mass and brightness, orbiting peacefully for billions of years. But often, the stars are unequal, and their interaction grows complex as they evolve. The key lies in the Roche lobe, the teardrop-shaped region around each star within which its gravity dominates. If one star expands beyond its Roche lobe, its gas can spill over to its companion. This process, called mass transfer, can profoundly alter the evolution of both stars. Consider a system of 2 stars, one massive, the other smaller. The massive star evolves more quickly, swelling into a red giant. If it overflows its Roche lobe, gas streams onto its companion, forming an accretion disk around it. This stolen material may increase the mass of the companion, rejuvenating it and making it appear younger, a blue straggler. Trigger nuclear outbursts on the surface of a white dwarf companion, producing a sudden brightening known as a nova. Push the white dwarf over the Chandrasekhar limit, causing it to collapse and explode as a Type Ia supernova. In each case, mass transfer transforms the star's destinies, creating phenomena impossible for isolated stars. A nova occurs in a binary system, where a white dwarf accretes material from a companion star. Hydrogen builds up on the white dwarf surface until it ignites in a runaway fusion reaction. The result is a dramatic increase in brightness, sometimes by thousands of times, lasting weeks or months. Unlike supernovae, novae do not destroy the white dwarf. The process can repeat many times, with the white dwarf flaring again and again as it siphons more fuel. These systems remind us that even stellar corpses can reawaken under the right conditions. If the accreting white dwarf gathers enough mass to exceed the Chandrasekhar limit, 1.4 solar masses, its core collapses. Carbon fusion ignites explosively, unbinding the star in a Type Ia supernova. These explosions are extraordinary for 2 reasons. They are among the most energetic events in the universe. They occur with nearly uniform brightness, making them standard candles. Astronomers use Type Ia supernovae to measure cosmic distances. mapping the scale of the universe itself. In the late 1990s, observations of these supernovae revealed that the universe's expansion is accelerating, the first evidence for what we now call dark energy. Thus, the fate of a binary system of stars has led us to one of the greatest mysteries in cosmology. In some binaries, both stars are massive enough to end as neutron stars. If the system survives their violent supernovae, the neutron stars continue orbiting one another. Over millions of years, they spiral inward, radiating energy as gravitational waves. When they finally merge, the collision produces bursts of gravitational waves and electromagnetic radiation detectable across the cosmos. The landmark detection in 2017 confirmed that such mergers are also a major source of heavy elements like gold and platinum. This discovery showed that binary stars are not only spectacular in death, but also crucial to the cosmic chemical inventory. Another exotic outcome occurs when one member of a binary becomes a black hole. If it accretes material from its companion, the gas forms a hot accretion disk, emitting powerful X-rays. These X-ray binaries are among the best evidence we have for the existence of stellar mass black holes. From Earth, they appear as flickering X-ray sources, their signals carrying the signature of matter falling into darkness. The presence of a companion radically alters how a star evolves. A solitary star follows a predictable path, determined primarily by its mass. But in a binary, mass transfer, tidal forces, and collisions complicate the story. Some stars that appear young are actually ancient, rejuvenated by stolen mass. Others meet violent ends they never would have faced alone. This makes binaries not just fascinating curiosities, but essential tools for testing our models of stellar physics. Interestingly, our sun appears to be solitary, yet studies suggest it may have been born in a cluster with many siblings. Some astronomers even speculate that it once had a distant binary companion long since lost to the galaxy. If true, this might explain patterns in the outer solar system. Whether or not the sun once had a partner, it serves as a reminder that solitude among stars is not the rule, but the exception. Binary stars show us that the universe is a place of interaction, not isolation. Stars pull on each other, share mass, and sometimes destroy one another in their gravitational embrace. Out of these dances come novae, supernovae, X-ray binaries, gravitational waves, phenomena that shape galaxies and reveal cosmic truths. The story of binary stars is a story of companionship, rivalry, and destiny, written in light and gravity. It is a reminder that even in the vast emptiness of space, stars often find partners, and together they create wonders far greater than they could alone. The death of massive stars give rise to some of the most bizarre and fascinating objects in the cosmos. While white dwarfs are strange enough, Earth-sized stars made of degenerate matter neutron stars push physics even further. Within their tiny, ultra-dense forms lie conditions that defy laboratory experiments, revealing realms where quantum mechanics and relativity collide. Among these remnants are exotic subtypes, pulsars, and magnetars, whose extraordinary behaviors continue to astonish astronomers. When a massive star collapses in a supernova, its core may compress into a neutron star. With masses up to about twice that of the Sun, crammed into a sphere only 20 kilometers across, neutron stars are cosmic paradoxes. Tiny, yet immensely massive, fragile, yet indestructible. Inside, matter exists in forms we cannot reproduce on Earth. Atoms are crushed, electrons and protons merge into neutrons, and the star becomes one gigantic atomic nucleus. Some theories even suggest exotic states of matter within, such as quark matter, where neutrons themselves dissolve into a sea of fundamental particles. In 1967, astronomer Jocelyn Bell Burnell noticed strange, regular radio pulses from space. At first dubbed LGM for Little Green Men, these signals turned out not to be alien messages, but the beacons of pulsars rapidly rotating neutron stars. As neutron stars spin, their magnetic fields funnel charged particles into beams of radiation that sweep across space like lighthouse beams. When Earth lies in the path of one of these beams, we detect a pulse astonishingly regular, often more precise than atomic clocks. Some pulsars rotate hundreds of times per second, their speeds dizzying yet stable. These millisecond pulsars are often recycled, spun up by accreting matter from a binary companion. Pulsars are more than cosmic curiosities. They serve as natural laboratories for physics, allowing us to test Einstein's theory of general relativity, measure cosmic distances, and even search for gravitational waves through tiny variations in their timing. If pulsars are lighthouses, magnetars are cosmic dragons. These rare neutron stars possess magnetic fields 1,000 times stronger than ordinary pulsars, trillions of times stronger than Earth's. Such fields are so intense, they can distort atomic structures and even affect the vacuum of space itself. Magnetars reveal their power through bursts of high-energy radiation. Occasionally, they produce giant flares that release more energy in a fraction of a second than the sun emits in 100 years. These events are so bright they can momentarily affect Earth's upper atmosphere, even from tens of thousands of light years away. Scientists believe magnetars are short-lived, their extreme fields decaying within tens of thousands of years, a blink of cosmic time. Yet, in their brief lives, they are among the most powerful engines in the universe. Neutron stars, pulsars, and magnetars may not be the end of the story. Theoretical physics predicts other exotic remnants. Quark stars. If pressures inside a neutron star are high enough, neutrons may break down into their constituent quarks, producing an even denser object. Strange stars, a hypothesized state of matter involving strange quarks, potentially stable under extreme conditions. Boson stars, entirely hypothetical, composed not of normal matter, but of fundamental particles called bosons. None of these have been confirmed, but they represent the frontier of astrophysical speculation. Discovering such objects would revolutionize our understanding of matter and the universe. When neutron stars exist in binary systems, their orbits gradually decay as they radiate energy through gravitational waves. Eventually, they collide in a cataclysmic merger. In 2017, astronomers detected both gravitational waves and light from such an event, marking the dawn of multi-messenger astronomy. These collisions produce bursts of gamma rays, kilonova explosions, and most importantly, forge heavy elements like gold, platinum, and uranium. The very jewelry we wear, the technology in our electronics, and even the chemistry of our planet are tied to the extreme physics of neutron star mergers. Stellar exotica are not just bizarre remnants, they are natural laboratories where physics is pushed to extremes. Pulsars allow us to test relativity. Magnetars probe the limits of magnetic fields, and neutron stars challenge our understanding of matter at nuclear densities. By studying these objects, astronomers bridge the gap between astrophysics, quantum mechanics, and cosmology. They force us to confront questions about the nature of matter, energy, and the universe itself. While stars like the sun end quietly as white dwarfs, the universe also produces these spectacular remnants, pulsars ticking like cosmic clocks, magnetars flaring like celestial tempests, and neutron stars merging in fireworks of heavy elements. Together, they remind us that the cosmos thrives on extremes. It is not only a place of gentle light, but also of violent power, where the fabric of matter and space is stretched to its limits. Stars are not born alone. When a star ignites in the heart of a collapsing molecular cloud, it is almost always surrounded by a swirling disk of gas and dust. Within this disk, new worlds begin to take shape. Over time, the debris left over from star formation coalesces into planets, moons, asteroids, and comets. It is in these planetary systems that the conditions for oceans, atmospheres, and ultimately life can emerge. When a dense clump of gas collapses to form a star, not all material falls straight inward. Because the cloud has some initial spin, conservation of angular momentum forces the leftover gas and dust into a rotating, flattened protoplanetary disk around the young star. These disks can extend for hundreds of astronomical units, glowing in infrared light. Observations with telescopes like ALMA, the Atacama Large Millimeter, Submillimeter Array have revealed stunning images of disks with rings, gaps, and spirals, the fingerprints of planets already taking shape. The disk is a chaotic nursery, filled with turbulence, collisions, and heating from the central star. Yet out of this apparent disorder emerges order, a planetary system. Planet formation begins with dust grains, microscopic bits of silicates, carbon, and ices floating in the disk. Through gentle collisions, these grains stick together, forming larger clumps. Over time, these grow into planetesimals kilometer-sized building blocks. As planetesimals collide and merge, gravity becomes stronger, accelerating their growth into protoplanets. Eventually, some grow massive enough to dominate their orbits, sweeping up material and becoming full-fledged planets. This process called accretion can take millions of years. It explains why planetary systems often contain both small rocky worlds and massive gas giants, depending on conditions in the disk. Not all regions of the disk are equal. Temperature plays a decisive role. Close to the star, heat drives off volatile elements, leaving behind silicates and metals. Here, rocky planets like Earth, Venus, and Mars form farther out, beyond the snowline. Ices can survive. In these cold regions, protoplanets can grow large enough to capture thick atmospheres of hydrogen and helium, becoming gas giants like Jupiter and Saturn. This division explains why planetary systems often feature inner rocky worlds and altered giants. Yet every system is unique, and exoplanet discoveries have revealed incredible diversity far beyond what our solar system suggests. In the last few decades, astronomers have discovered thousands of exoplanets, planets orbiting stars beyond our sun. Many were found by the Kepler Space Telescope, which measured tiny dips in starlight as planets pass in front of their stars. Others were detected through radial velocity measurements, gravitational microlensing, or even direct imaging. The results have been staggering. Hot Jupiters, gas giants orbiting closer than Mercury does to the Sun, super-Earths, rocky worlds, larger than Earth but smaller than Neptune, mini-Neptunes, intermediate planets with thick atmospheres. These discoveries reveal that planetary systems are incredibly diverse, and that planets are likely more common than stars themselves. Among all these worlds, astronomers focus special attention on those in the habitable zone, the region around the star, where temperatures allow liquid water to exist on the surface. But habitability depends on much more than distance. A planet must be large enough to retain an atmosphere. It must not be too massive, or it will become a gas giant. The star itself must be stable, providing steady light and heat. Small, long-lived stars like red dwarfs may host habitable planets for trillions of years, far longer than sun-like stars. Yet, they are prone to powerful flares, which could strip atmospheres. The balance is delicate, and life may emerge only under very specific conditions. Stars not only give planets light and warmth, but also supply the raw ingredients of life. Elements like carbon, nitrogen, and oxygen are forged in stellar interiors and distributed by supernovae. Without generations of stars living and dying, planets will lack the chemistry needed for biology. Even now, stars influence life. The sun powers Earth's climate, drives photosynthesis, and sustains the biosphere. Too much or too little stellar energy, and life as we know it could not exist. Planetary systems include more than planets. Moons can provide additional habitats, as in the case of Europa and Enceladus, icy moons with subsurface oceans. Comets and asteroids carry water and organic molecules, possibly seeding young planets with the precursors of life. In this way, the formation of planets is not just about worlds themselves, but about a complete ecosystem of bodies, each playing a role in the cosmic story of habitability. The Sun's protoplanetary disk gave rise to a family of 8 planets, dozens of moons, countless asteroids, and icy comets. Over billions of years, this system has evolved into a complex and stable arrangement that sustains life on Earth. Our system is only one example among billions, but it shows how stars naturally give rise to worlds and how those worlds can, under the right conditions, become homes for living beings. Stars, by their very nature, are creators. They are not only the forgers of elements, but also the architects of planets and, ultimately, the enablers of life. Every atom in our bodies was once part of a star, and every heartbeat is powered by the energy of a sun. For centuries, humans have looked up at the night sky and wondered, are we alone? The billions of stars scattered across the universe raise an equally staggering question: how many of them might host planets with life? In recent decades, the discovery of exoplanets and the study of stellar environments have brought us closer than ever to answering that question. Stars, as the creators of worlds and the providers of light, are at the heart of the search for extraterrestrial life. Since the first confirmed exoplanet detection in the 1990s, astronomers have cataloged thousands of planets orbiting distant stars. These discoveries have reshaped our view of the cosmos. Planets are not rare exceptions, but a natural byproduct of star formation. Most stars are now believed to host planets, and many host multiple. This means that the Milky Way alone, with over 100 billion stars, likely contains hundreds of billions of planets. Among them, countless worlds may lie within the habitable zone of their stars. Where conditions could support liquid water, the habitable zone is defined by distance from the star. Too close and water boils away. Too far and it freezes. Earth sits comfortably in the sun's habitable zone, but the concept is more nuanced than simple distance. The star's type matters. Massive stars burn hot and bright, but live short lives, giving little time for life to evolve. Sun-like stars offer billions of years of stable conditions, making them prime candidates for hosting life-bearing worlds. Red dwarfs, the most common stars in the galaxy, provide trillions of years of longevity, but their violent flares may strip planets of atmospheres, posing a challenge to habitability. Thus, while many stars have habitable zones, not all offer safe harbors for life. The star itself shapes the prospects of its planets. Finding planets is one step, finding life is another. Astronomers search for biosignatures, chemical clues in planetary atmospheres that may indicate biological activity. On Earth, oxygen is the most obvious biosignature, produced by photosynthesis. Methane, nitrous oxide, and other gases can also suggest life when found in unusual combinations. Future telescopes, such as the James Webb Space Telescope already active and the upcoming Extremely Large Telescope ELT, are designed to study exoplanet atmospheres in detail. By observing starlight filtered through a planet's atmosphere during transits, scientists can detect the fingerprints of molecules. The ultimate goal is to identify a living atmosphere, a mix of gases that cannot easily be explained by geology or chemistry alone. Stars influence not only the position of the habitable zone, but also the stability of planetary environments. Stellar activity, flares, winds, and radiation can strip atmospheres, sterilize surfaces, or, conversely, provide the energy needed for chemistry to spark life. Young stars tend to be volatile, bombarding planets with radiation. Life may need to wait until a star calms down. Old stars may expand into red giants, altering the habitable zone and dooming once habitable worlds. Binary stars add complexity, with planets orbiting one or both stars in dynamic environments. Thus, the search for life requires careful attention not just to planets, but to the stars that sustain them. Our own planet provides the best example of a life-bearing world. Earth orbits a stable, middle-aged star with enough mass to shine for billions of years, but not so massive that it burns out quickly. Its magnetic field shields it from solar winds, and its atmosphere retains water while balancing greenhouse gases. These conditions may be rare, or they may be common. Either way, Earth shows us what is possible and what astronomers should look for in alien systems. In 1961, Frank Drake proposed an equation to estimate the number of communicating civilizations in our galaxy. The formula considers factors like the number of stars, the fraction with planets, the number of habitable planets, the fraction where life emerges, and the fraction where intelligence evolves. While the values of many terms remain uncertain, discoveries of exoplanets have already changed the equation dramatically. We now know that planetary systems are ubiquitous and habitable zone worlds are likely in the billions. The great unknowns remain. How often does life appear, and how often does it develop intelligence? The search for extraterrestrial intelligence listens for artificial signals from distant stars. Radio telescopes scan the sky for patterns that cannot be explained by natural processes, while no confirmed signals have yet been found. The search continues. Even silence is data. It forces us to consider whether intelligent life is rare, short-lived, or simply beyond our current ability to detect. When we study stars and their planets in the search for life, we are also studying ourselves. The conditions that make Earth habitable, a stable star, protective atmosphere, liquid water, in time may be rare alignments in the universe, or they may be the natural outcome of stellar evolution. Every star we study brings us closer to an answer. Whether the galaxy is teeming with life or whether Earth is unique, the stars hold the key. The search for life among the stars is not just a scientific pursuit but a philosophical one. It challenges us to consider our place in the cosmos. Are we a singular miracle or one of countless living worlds? Whatever the answer, the journey itself transforms us. By studying stars and their planets, we learn not only about the universe, but also about the fragility and wonder of life on Earth. Stars, for all their brilliance, are mortal. They live on timescales far beyond human imagination, but each eventually reaches an end. Yet stellar death is not simply an end, it is a transformation. In their demise, stars enrich the cosmos, leaving behind remnants that seed new generations of stars, planets, and life. The universe is a tapestry woven from the light and ashes of countless stellar lives. Low to medium mass stars, like our Sun, end their lives gently. After swelling to red giants and shedding their outer layers, they leave behind dense cores, white dwarfs. These remnants, no larger than Earth but holding half the Sun's mass, shine faintly with leftover heat. They slowly cool over billions of years, fading into theoretical black dwarfs, cold, dead stars that no longer emit light. Though quiet, these stars' deaths enrich their surroundings. The gas shed during the red giant phase creates planetary nebulae, glowing shells of material that spread carbon, oxygen, and other elements into space. Massive stars follow a more spectacular path. When nuclear fusion in their cores ceases, gravity overwhelms them, and they collapse in catastrophic explosions. Supernovae. In a single instant, a supernova can outshine an entire galaxy. Shockwaves blast through the interstellar medium, dispersing heavy elements forged in the star's core and in the explosion itself, elements essential for life, from iron in our blood to calcium in our bones. Supernovae are not only destructive, they're also creative. Their shockwaves can compress nearby clouds of gas, triggering the birth of new stars. Death begets birth, continuing the cosmic cycle. The remains of massive stars depend on their final mass. If the core left behind is between about 1.4 and 3 solar masses, it collapses into a neutron star, a city-sized object of unimaginable density. If the core is heavier still, it collapses further, forming a black hole, a region of space where gravity is so intense that not even light can escape. These remnants, though dark, profoundly shape their surroundings. Neutron stars become pulsars and magnetars, while black holes, power quasars, X-ray binaries, and gravitational wave events. Every star's death enriches the interstellar medium with heavy elements. Each new generation of stars forms from this recycled material, progressively more enriched. The first stars, population 3, were nearly pure hydrogen and helium. Later generations incorporated carbon, oxygen, silicon, and iron. Today, new stars form from gas, already laced with the ashes of countless predecessors. This recycling is why planets like Earth exist. Without multiple generations of stars dying, the universe would lack the materials needed for solid planets and for life itself. Stars and their deaths are integral to galactic evolution. Supernovae stir and heat galactic gas, regulating star formation. Stellar winds carve out bubbles and cavities, shaping the structure of galaxies. Black holes at galactic centers, likely the remnants of the earliest massive stars, influence the growth of entire galaxies through their powerful jets and outflows. Galaxies are not static star cities, but ecosystems where stellar life and death sustain the cycle of creation. Looking far ahead, the universe faces a gradual decline in star formation. In tens of billions of years, the gas needed for new stars will run out. In hundreds of billions of years, only long-lived red dwarfs will still burn, glowing faintly in the cosmic dark. In trillions of years, even they will die, leaving a universe of stellar remnants, white dwarfs, neutron stars, and black holes. The cosmos, once ablaze with starlight, will eventually fade into darkness. Even after the last stars fade, black holes will continue to shape the universe over unimaginable timescales. They will slowly evaporate through Hawking radiation, releasing their mass as faint radiation until nothing remains. In this distant future, the universe will be a thin soup of subatomic particles, stretched by expansion into near nothingness. Yet everything that ever lived, burned, or shone will have come from the fires of stars. Those stars are impermanent. Their legacy is eternal. They forged the elements, built the planets, and lit the skies. Their deaths recycled matter into new forms, making life possible. Every atom in your body was once inside a star. Every breath tied to the ashes of stellar generations. Stars may die, but in their death, they give birth to worlds, to life, and to the endless curiosity that leads us to look up and wonder. Their legacy is not just in the light they emit, but in the fact that without them, there will be nothing at all. When a star shines, it does more than illuminate the night. It launches countless photons, particles of light on journeys that may last billions of years. Some strike nearby planets, fueling life. Others wander through intergalactic space, crossing unimaginable distances. But what happens to this starlight in the long run? Does it last forever? Or does it, like stars themselves, have an end? A photon is born deep inside a star's core, in the furnace of nuclear fusion. Protons fuse into helium, releasing energy that emerges as gamma rays. Yet, the journey outward is arduous. Within the star's dense interior, photons scatter endlessly, absorbed and re-emitted by particles in a chaotic dance. For the sun, it can take tens of thousands, even hundreds of thousands of years for a photon created in the core to finally escape to the surface. When it does, it is no longer a gamma ray, but visible light, the gentle sunlight that reaches Earth. Thus, every beam of starlight carries within it the record of immense struggle, born in crushing density and freed into the cosmos. Once freed from its star, a photon embarks on a straight-line journey through space. In the vacuum, it travels at the ultimate cosmic speed limit, 299,792 kilometers per second. Unless absorbed by matter or bent by gravity, it will travel indefinitely. Some photons strike dust or gas, hitting interstellar clouds. Others are caught by planets, becoming warmth, photosynthesis, or even the spark of life. Many more simply keep going, carrying the story of their star across light years, even billions of light years. When we look up at the night sky, we are catching these ancient travelers. Each photon hitting our eyes began its journey long ago, some before humanity existed. In this sense, starlight is a time machine, delivering messages from the past. But the universe is not static. As space expands, so too does the wavelengths of light traveling within it. Photons stretch, their energy decreasing in a phenomenon known as redshift. Light from nearby stars remains largely unchanged. Light from distant galaxies is redshifted, appearing stretched into the infrared. Light from the earliest stars and galaxies is redshifted so much that it is now detected as faint microwaves. The entire universe is bathed in such ancient starlight, the cosmic microwave background relic radiation from the Big Bang itself. This redshift ensures that even if photons escape absorption, they lose energy to the stretching of space. Photons do not always travel in straight, unbent paths. Massive objects warp spacetime, bending the paths of lighting phenomena known as gravitational lensing. A galaxy cluster can bend the light of a more distant galaxy, creating multiple images. Black holes can bend starlight into rings or arcs. Even individual stars can act as lenses, briefly magnifying distant background stars. Thus, a photon's journey is shaped not only by distance and time, but by the invisible architecture of gravity. What becomes of starlight in the distant future, long after stars have died? The answer lies in the fate of the universe itself. As expansion continues, photons will stretch to longer and longer wavelengths. Visible starlight will fade into infrared, then microwave, then radio waves. Eventually, the wavelengths will be so long that photons carry almost no energy at all, lost in the cold darkness of an expanding cosmos. In the farthest epochs, when all stars are gone, starlight will not disappear suddenly, but fade into invisibility, stretched beyond usefulness. The universe will not end in fire, but in dimness. The last photons will be stretched into silence, leaving behind a dark, cold void. Yet even as starlight fades, its legacy endures. Every photon that strikes a planet, a rock, or a living being leaves an imprint. On Earth, sunlight has powered photosynthesis for billions of years, fueling evolution and civilization. The energy of starlight is woven into our food, our air, and our very cells. Even in the far reaches of space, starlight guides galaxies, warms planets, and creates beauty from nebulae glowing with scattered light to auroras dancing on planetary skies. Though photons themselves may be stretched into nothingness, their influence will have shaped the universe irrevocably. For now, we live in an age of brilliance. Stars fill the night, galaxies glow, and photons reach us across billions of light years. We can still see the light of the first galaxies, still study the radiation of the Big Bang. We exist in what might be called the era of starlight, a cosmic middle age when the universe is alive with energy. Someday, that light will fade, but today it defines our cosmos. Starlight is more than illumination. It is history, energy, and memory, the universe speaking across time. It reminds us that everything we see is fleeting, yet everything we are is born of light. Long before telescopes revealed their true nature, stars were among humanity's oldest companions. They filled the night sky with patterns, guided travelers across deserts and seas, and became symbols in myths, religions, and art. To our ancestors, stars were more than distant lights. They were gods, ancestors, omens, and mysteries. Even today, after centuries of science, stars continue to inspire awe, poetry, and wonder. Early humans looked up at the night sky without scientific explanations, but with deep curiosity. They saw stars move in predictable patterns, rising and setting with the seasons. This regularity made them natural calendars. By mapping the stars, ancient peoples tracked time for agriculture, navigation, and ritual. The Pleiades marked planting seasons in many cultures. The rising of Sirius in Egypt signaled the annual flooding of the Nile, essential for farming. The sky became the first textbook of civilization. To make sense of the stars, humans wove them into stories. Constellations turned random points of light into hunters, animals, and heroes. In Greece, Orion the hunter strolled across the sky. In China, the celestial dragon stretched across constellations. In indigenous American traditions, stars became animals and spirits tied to the cycles of nature. These myths were more than entertainment. They encoded knowledge passed down across generations. A constellation might tell when to plant crops, when rains will come, or how to navigate to distant lands. The stars were memory written in the heavens. For many cultures, stars were divine. The Babylonians saw them as the homes of gods. The Maya linked Venus with war and prophecy. Polynesians believed ancestral spirits shone as guiding stars. Even monotheistic traditions preserve the sacredness of stars. In the Hebrew Bible, stars are described as countless and eternal. In the Quran, they are lamps in the sky. Christian nativity stories center around a star guiding the wise man. Across traditions, stars symbolize permanence, destiny, and guidance. They were the unchanging background against which human life played out immortal lights in a mortal world. Stars were not only symbols, but practical tools. For millennia, sailors navigated by the night sky. The North Star, fixed in the northern sky, guided travelers across oceans and deserts. Polynesian wayfinders crossed vast stretches of the Pacific using only star patterns, ocean swells, and wind. Without stars, the great migrations and explorations that shaped human history might never have been possible. There were compasses long before compasses existed. As civilizations grew, so too did curiosity about the nature of stars. Greek philosophers like Anaximander and Aristarchus speculated that stars were distant suns. Islamic scholars preserved and expanded Greek astronomy, naming many of the stars we still use today. In the Renaissance, Galileo's telescope revealed that the Milky Way was not a cloud, but countless stars. With each discovery, stars shifted from divine symbols to physical worlds. This did not lessen their wonder, but deepened it. The realization that stars are suns, perhaps with planets like Earth, transformed philosophy and raised new questions. Are we alone? Is the universe infinite? Stars have long been muses for artists and poets. Shakespeare called them fireflies of heaven. Van Gogh's Starry Night swirls with cosmic intensity. Countless lullabies, songs, and poems use stars as metaphors for hope, love, or eternity. Even in modern times, we speak of reaching for the stars to symbolize ambition or call loved ones our stars. They remain cultural anchors, linking the human heart to the cosmos. Science reveals stars to be nuclear furnaces, forging elements and shaping galaxies. Yet instead of stripping away their magic, this knowledge only enriched it. To know that the iron in our blood and the oxygen in our lungs were created in stars is to connect myth to reality. The ancient intuition that stars were linked to life was, in a sense, correct, just not in the way they imagined. Carl Sagan's famous phrase, "We are made of star stuff," distills this truth into poetry. Stars are not merely symbols of eternity, they are our ancestors, in the most literal sense. The way we view stars reflects our own evolution. To early humans, they were divine. To sailors, they were guides. To poets, they were metaphors. To scientists, they are laboratories of physics. To philosophers, they are reminders of our smallness and our potential. Even as city lights dim the night sky for much of the modern world, the symbolism of stars remains. We put them on flags, awards, and even rating systems. They remain icons of excellence, guidance, and wonder. Across cultures and ages, stars have always carried one unifying role. They make us wonder, what are they? Where did they come from? Are we alone among them? In asking these questions, humanity defines itself. We're not just creatures who live under the stars, we are creatures who ask about them, who tell stories about them, who dream of reaching them. The stars, then, are more than astrophysical objects. They are part of what makes us human. They link the practical with the poetic, the scientific with the spiritual. They remind us that the universe is vast, that our lives are brief, and yet that our minds can stretch as far as the stars themselves. Throughout this journey, we have followed stars from their humble beginnings in cold molecular clouds to their brilliant lives and spectacular deaths. But stars do not exist in isolation. They are born, live, and die within galaxies' vast cosmic ecosystems where billions, sometimes trillions, of stars interact with gas, dust, dark matter, and black holes. The life cycle of stars is inseparable from the life cycle of galaxies, and together they point toward the ultimate destiny of the universe. A galaxy is more than a collection of stars. It is a living, evolving system in which gas clouds give birth to stars. Stars enrich the gas with heavier elements, and stellar explosions regulate the balance of matter and energy. Spiral galaxies, like our Milky Way, are star factories, with swirling arms filled with young, blue stars and glowing nebulae. Elliptical galaxies are older and quieter, dominated by ancient red stars with little star-forming gas left. Irregular galaxies are shaped by collisions and turbulence, chaotic but fertile. In each case, the stars within form part of a continuous cycle of creation and destruction, feeding back into the galactic whole. The deaths of massive stars through supernovae and stellar winds are essential to galaxies. They return enriched material to the interstellar medium, ensuring that future stars and planets contain the heavy elements needed for life. Supernova shockwaves also compress nearby clouds, triggering new waves of star formation. At the same time, they can blow gas out of galaxies, slowing star birth. This balance between feedback and replenishment determines the galaxy's character. Galaxies are not static star cities, but dynamic, evolving systems, their appearance and destiny, shaped by the lives and deaths of stars. At the heart of nearly every large galaxy lies a supermassive black hole, millions to billions of times the mass of the sun. These gravitational monsters influence far more than their immediate surroundings. When actively feeding, they power quasars' brilliant beacons visible across the universe. Their jets and radiation can heat or expel galactic gas, shutting down star formation. In this way, black holes regulate the growth of galaxies, linking the smallest scales of stellar remnants to the largest structures in the universe. Paradoxically, black holes born of stellar death play a role in shaping whether new stars can form. Galaxies are not isolated islands. They interact, collide, and merge in cosmic slow motion. These encounters reshape galaxies, spark intense bursts of star formation, and sometimes funnel gas into central black holes. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two will merge into a new galaxy, sometimes called Milkomeda. During the merger, stars themselves will rarely collide, but their gravitational interactions will fling many into new orbits, and tidal forces will ignite waves of star birth. In this way, galactic evolution is intimately tied to stellar evolution, as collisions recycle material and reconfigure cosmic architecture. Despite these cycles, the universe's star formation rate has been declining for billions of years. In its youth, the cosmos blazed with new stars, fueled by abundant cold gas. Today, galaxies are running low on raw material. Over the next tens of billions of years, star formation will continue to slow. Galaxies will grow redder and quieter as young blue stars die off, leaving only long-lived red dwarfs. The universe is gradually transitioning from a vibrant, star-filled epoch into one dominated by stellar remnants. Looking trillions of years ahead, red dwarfs, the longest-lived stars, will eventually exhaust their fuel, leaving white dwarfs. White dwarfs will cool into black dwarfs, dark and inert. Neutron stars and black holes will remain silent remnants of a more luminous age. Galaxies will no longer glitter with stars, but drift as dark collections of remnants, their gas depleted. The cosmic web of galaxies, once lit with billions of suns, will fade into shadow. The destiny of galaxies and of stars within them is tied to the fate of the universe itself. If cosmic expansion continues to accelerate, galaxies will drift farther apart, their light redshifted into invisibility. Star formation will cease entirely, and the universe will grow colder and darker in the heat-death scenario. Alternatively, if unknown physics alters expansion, other endings are possible: a big crunch, a big rip, or endless cycles of birth and collapse. In all cases, stars and galaxies are central, either fading into darkness or reborn in new universes. Whatever the ultimate fate, the present universe is uniquely luminous. We live during the golden age of stars, when galaxies are still fertile and skies still bright. Future epochs will lack this brilliance, their histories written in relics rather than in starlight. In their time, stars and galaxies have given rise to planets, life, and consciousness. They have forged the elements, shaped the cosmos, and filled it with beauty. Their destiny may be darkness, but their legacy is eternal. They made the universe what it is. We began with a question that seems almost impossible. How do stars form from nothing? And yet, we have seen how the universe itself, from its earliest moments, set the stage for starlight. Out of the emptiness of space, hydrogen and helium gathered. Gravity worked its invisible pull, and light was born in the darkness. Stars, these immense furnaces of matter and energy, emerged from chaos, order carved out of void. But the story of stars is not just astrophysical. It is existential. In following their journey, we discover not only the mechanics of fusion and gravity, but also the story of life, death, rebirth, and meaning on cosmic scales. In the cold cradles of molecular clouds, random fluctuations grew into collapsing cores. Gravity took hold, pulling dust and gas inward. Disks formed, and in their centers, pressure and temperature ignited fusion. What was once formless became radiant, a star. This process repeats across the galaxy, as it has for billions of years. Stars emerge from nothing, not literal void, but diffuse gas so thin it would seem like nothing to us, and transform it into blazing light. Once born, stars live in delicate balance. Fusion pushes outward, gravity pulls inward, and for millions or billions of years, they shine steadily. They differ in size and brightness, from tiny red dwarfs burning slowly to massive blue giants racing toward explosive ends. Each star writes its own story in light, yet all follow the same arc: formation, equilibrium, and eventually decline. Stars are not eternal. The small ones fade quietly, leaving white dwarfs. the massive ones explode in spectacular supernovae, scattering their guts across the cosmos. Their remnants, neutron stars, pulsars, magnetars, black holes, continue the tale in bizarre and extreme forms. But even in death, stars give more than they take. Their explosions forge heavy elements. Their winds and remnants enrich the interstellar medium. They recycle matter into the raw material of future stars, planets, and life. Every atom in your body, from the calcium in your bones to the oxygen in your lungs, was born in a star. You are, in the most literal sense, the child of starlight. Stars are architects of worlds. Around them, disks of dust and gas give rise to planets, moons, asteroids, and comets. These planets can become habitats, with atmospheres, oceans, and the chemistry for biology. Somewhere in this process, life arises. On Earth, it did so quickly, fed by sunlight and nurtured by the stability of a middle-aged star. Perhaps it has elsewhere, too, on worlds orbiting distant suns, where alien skies glow with alien constellations. Thus, stars are not just cosmic furnaces. They are enablers of life, the bridge between physics and biology, between matter and meaning. Stars gather in galaxies, vast communities bound by gravity. Within these star cities, cycles of birth and death shape the whole. Black holes at the centers govern flows of energy, while collisions and mergers reshape destinies. The Milky Way is one such city, and our sun is but one among hundreds of billions of residents. Beyond it lie trillions more galaxies, each with their own histories, their own stellar stories. The universe is not just full of stars, it is defined by them. But even stars have limits. The era of star formation is slowing. In tens of billions of years, the cosmos will exhaust its gas reserves. Red dwarfs, the most patient stars, will outlast the rest. But eventually, they too will fade. Trillions of years from now, the universe will be filled only with stellar remnants, white dwarfs, neutron stars, and black holes. Starlight will grow dimmer, stretched by cosmic expansion into invisibility. The brilliant age we live in, the era of stars, is temporary. We are lucky to exist in this luminous chapter of cosmic history. Yet, for us, stars are more than astrophysical phenomena. They are symbols, guides, and inspirations. They shaped our myths, navigations, religions, and philosophies. They inspired explorers to cross oceans, artists to paint skies, and scientists to build telescopes. Most importantly, they gave us life. Without stars, there would be no Earth, no oceans, no air, no humans to ask questions about the universe. To understand stars is to understand ourselves. The story comes full circle. Stars form from nothing, from clouds so thin they are nearly void. Yet they create everything. Matter, light, planets, life, culture, and consciousness all flow from stellar fires. The next time you look up at the night sky, you are not just looking at points of light. You are looking at the engines of creation, the ancestors of life, the storytellers of the cosmos. Stars are reminders that from emptiness can come brilliance, from chaos can come order, and from finite lives can come eternal legacies. And so, we end where we began, with wonder. The stars do not just answer questions of science. They pose questions of meaning. Why does the universe create light? Why does matter organize itself into life? Why do we, fragile beings, have the ability to look up and ask? Perhaps the ultimate answer lies not in physics or philosophy, but in the stars themselves. For in their glow, we see both what we are made of and what we are destined to return to. The endless cycle of creation and transformation. The stars formed from nothing, and from them, everything came.